Okay, section 1.5 is on homogeneous systems, and um, this is any system. If I, have my A11x1 plus A12 x2 plus out here to A1n xn. If that equals 0, if the right-hand side of all of these is equal to 0, so I'll put in my second row A2n xn equals 0, and again we go down to am1, x1 plus am2 x2 plus all the way out to amn xn equals 0. Okay, so if we have a system like this, the right-hand side here is 0 everywhere. That is a homogeneous system. And as such, notice that the solution x1, well, actually, I want to write it as x1 equal, x2 equal, x3, all the way out here to xn equals 0 is always a solution, and is called the trivial solution. So, if I see the right-hand side is always zeros, then I know there's at least one solution, a trivial solution. And then really all they do in this section that's any different is talk about non-trivial solutions. So, a non-trivial solution is one that has at least one non-zero element. Okay, so as an example, if you look at x minus y equals 0 and x plus y equals 0, and we go to our 1, minus 1, 1, 1, 0, 0, like that. So there's our augmented matrix. We do our first row reduction. We'll have 1, minus 1, 0. Notice the right-hand side will always stay 0. Nothing ever changes there. And so here we'll get 0 and 2 and 0. And so if I reduce that again, I get 1, minus 1, 0, 0, 1, 0. And then finally, my last one here. So this was the first one, second one, third one, fourth one. Now in this one, I'm not showing how I'm doing these. On an exam, you will want to show how you did it, unless you're allowed to use technology to do it, and then you're going to want to state that you use technology. But for now, we just show this, and so this tells us that we get this unique solution of x equals 0, y equals 0, and so it's only the trivial solution. But on the other hand, if you have x minus y plus z equals 0, and x plus y plus z equals 0. Then once again we have 1 minus 1, 1, and 0, 1, 1, 1, and 0. So there's our augmented matrix that we start with. Subtract the first row from the second row, and we've got 1, 1, 1, 0, and 0, 2, 0, 0, like that. And so then our third one will reduce that to 0, 1, 0, 0. And finally, again, we'll add the second row to the first row, and we get 1, 0, 1, 0, 0, 1, 0, 0. And so you see in this case, we do have that our y is equal to 0, but x is equal to negative z, or x plus z equals 0. And so then we get x equals negative z, and so z is arbitrary, which would mean a non-trivial solution is, I could let z equal 1, so x would be negative 1, so that'd be negative 1, y equals 0, and then z equals 1. So there's a non-trivial solution, okay? And they just give us the theorem, this theorem 1.5.1, that a homogeneous system okay, so if we have one of these with or in n unknowns, okay, so n variables, and m equations. Typically, I guess I should write that the other way, but somehow I wrote it that way. I don't know. So usually you'd say m equations and n unknowns. Usually you would. Why I didn't, I don't know. A homogeneous system in n unknowns and m equations has a non-trivial solution. Actually has an infinite number, but has a non-trivial solution if m is less than n. So if there are more variables, more unknowns than equations, there's a non-trivial solution. And now they go through the proof on this, and it's just a number sort of thing. Okay, so we say suppose m is less than n, then think about, so my dog sits right beside me, and really we weighed her the other day. She was 94 pounds, not quite a year old yet. She's a big one. And okay, so anyway, so suppose m is less than n, and that coefficient matrix is equivalent to some row reduced form. Then let's kind of look at what happens here, right? So here are my rows, 1, 2, 3 to m, and I'm going to have a 1 with a bunch of zeros, all right, down like that. And now, you know, I may have, who knows, a 2 there and so forth, you know, and maybe a 0 there. And so these would all have to be zeros down to here. And, you know, maybe that's a 1 and then zeros down to there, right, to get my reduced row echelon form. Now notice that what's going to happen is the most rows I could have, the number of non-zero rows, right? Because, you know, at some point then I just get all zeros maybe, okay, and over to here. Okay, and I'll be looking for these ones. Well, I could have a 1 in every row, but so the most is m. And so if I let r be the number of non-zero rows, okay, non-zero rows, then what we see is, you know, r has to be less than m, which is less than or equal to m, and which has to be less than n. And so then if I take n minus r, right, n minus r has to be bigger than 0 since r is strictly less than n. And in that n minus r is the number of arbitrary unknowns. But that's greater than 0. Okay, so there has to be at least one arbitrary unknown. And in that case, since there's at least one arbitrary unknown, set it equal to 1. You know, set one arbitrary unknown to 1, and we have a non-trivial solution. So there we go. So that's the idea. So again, just if you have this homogeneous system, something like this, then we always know we'll have at least one solution. It's never inconsistent. We've always got at least the trivial solution, but then the question might be, well, does it have any non-trivial solutions? Okay, and that does in chapter 1.